Hey everyone, on this lesson we are going to study subnetting in IP networks. We are now at this point of the syllabus on addressing and subnetting. And first of all, let's introduce the idea of subnetting. So what is subnetting? Well, the essential idea is from a single network address to build multiple networks meeting a set of requirements. For example, an ISP, an internet service provider, provides a range of addresses to a company to connect to the internet, and from this range we can apply subnetting. For instance, suppose that this range is this one given. So some important notions. First of all, given this range, how many hosts can be connected to this network? And this is a question that commonly arises, and the key to answer this is we must look at the mask of this IP address. So the mask is 16. So if we have 16, okay, on the mask, this means that we have the same amount of bits for the net ID and the same for the host ID, right? Because this mask here represents the number of bits of the net ID. And so if we know that in an IP address we have 32 bits, then if we subtract 16 from 32, we also have 16. This is why here we can also conclude that we have 16 bits for the host ID. So the number of bits that we have on the host ID is very important to know how many hosts can be connected to this network, right? So since we have 16 bits, in principle, we could consider that we can have 2 raised to 16 number of hosts, so all of the possible combinations of zeros and ones, right, on this binary number of the host ID. However, remember that we have 2 IP addresses that are special, they are specific, and they are also reserved for the network address and the broadcast address. So we need to subtract from this amount of hosts these 2 IP addresses. Very well, so with this remains with 65,534 different IP addresses to set the host ID. So this is going to be the number of possible hosts that can be connected to this network. But what happens? It doesn't make any sense to have only one network. Just imagine only one network with this number of hosts. These are many hosts, and if we only have one network, this is more likely not to be feasible, because a number of hosts like this one inside a physical network near the same area, okay, is a very high value. So this is when the subnetting comes into place. So subnetting is used. With subnet, what we do is we extend the net ID, okay, and we occupy more bits. This is called the subnet ID. So we are on the same example. Remember that we have the first 16 bits of this IP address, okay, represent the net ID, the network identifier. And since we know that each decimal that we see here, each decimal value has 8 bits, then we have here that the first 2 decimal values represent the net ID, right? So these first 16 bits, these first 2 decimal values represent the network identifier, and then the remaining bits, right, the remaining that we have here, the 16 bits, is the host ID. Represent the host ID. So with subnetting, what we do is we extend the net ID, okay, and we occupy more bits of the host ID to include inside what is called the subnet ID. And with this idea, we can build multiple networks from a single network. So let's now look more closely at this example. So what we're doing here is from the 16 bits of the net ID, okay, we are also adding 8 bits of the host ID to include inside the net ID. So we will have now 8 bits of the subnet ID. So if we sum 16 plus 8, we get a value of 24. So now the net ID of each of these multiple networks, right, will have 24 bits. Now 24 bits is going to be the net ID. For example, we can now create multiple networks, okay, multiple different networks, and all of them will have 24 bits for the net IDs instead of 16 that we had before. For example, here we can set all of these 8 bits of the subnet ID to be 0. So now this network ID, this network identifier, is going to be this one in here, right? What we had before, 847.8.0. Right? This 0.0 is because we are adding here these 8 bits of the subnet ID. Then we keep doing this over and over. Now the next one, since each net ID will identify a different network, since each of them is going to identify a different network, they must be different. That's why here we just need this network to be different. So here the subnet ID, we basically add a 1, so now we have 0.1. Here we add the 1 at index that we see here. So remember that this value here in binary is equal to 2 in decimal, because 1, 0 represents the value 2 in decimal. Remember, to convert a binary number to decimal value is very simple. We just here select the indices. Since we have 8 bits, we'll have the indices from 0 to 7. And here we only select those that have the value 1. Here we only have the value 1, okay, on the index 1. All of the remaining, the rest are 0, so we're not interested. So we take base 2 because we are now analyzing combinations of 0 and 1, and now the index 1, this is the exponent. So 2 raised to 1 is 2, that's why here the value is 2. And this is why we see here that on this network identifier, on the decimal representation, we have the 0.2. The same here from the 0.3, this value here of the subnet ID, the last 2 bits are 1, 1, so here we have, instead of 1, 0, we have 1, 1, so now we select here this 1, so 2 raised to 0, okay, plus 2 raised to 1. Both of the indices are 1, so we select both, so this is 1 plus 2, which gives us 3, right? Basically, and simple conversion between binary values and decimal values. And we can do this over and over, and we can create multiple different network identifiers, and all of them will have 24. 24 bits for the net ID. Now keep in mind, since on these new networks, since each network ID will be of 24 bits, what is going to be the number of bits of the host ID? Well, very simple, 32 minus 24, so we have 8, right? We will have 8 bits of the host ID, these ones that we see here, only 8. Okay, so staying on this same example of the internet service provider that provides this range of addresses to the company to connect to the internet. After applying subnetting, we can here have different networks, all of them with a mask of 24. As we can see, all of these networks have a mask of 24 because their net ID occupies 24 bits, right, after applying this subnetting. So how many networks have been created by doing this process? Well, here, since we have added 8 bits for the subnet ID, right? These 8 bits in here that we're including to be part of the subnet ID, then we will have 2 raised to 8, right? 2 to the power of 8, so we will have 256 net IDs, right? Different net IDs. So this implies that we will have 256 networks. Basically, remember, the number of different net IDs that we can have is the number of different networks that we can have, because a net ID identifies a network. Okay, now a second question: how many hosts will each network have at most? Well, here it is important to consider that now, in this case, since before we had 16 bits and we basically took 8 of these 16 to be part of the net ID, okay, we've lost bits of the host ID. Now we only have 8 bits of the host ID. Therefore, at most, each network can have 2 raised to 8 host IDs, so 256 different host IDs, so different hosts. And also very important, we have to subtract 1, okay, of the network address and also 1 of the broadcast address. Very important not to forget this. So at the end, all in all, what we can conclude is that how many hosts will each network have at most? Well, at most, each network will have 254 different IP addresses. So here, each network will have 254 different hosts. Very important here not to forget to subtract 1 IP of the network address. This is the case where all of the bits of the host ID are 0, and also 1 of the broadcast address, where all of the bits of the host ID are 1. This is something that we already studied before. So now, at the end, in total, how many different IP addresses will there be? Well, to compute this is very simple. We basically multiply the number of networks that we have with the number of hosts, right? The number of different IP addresses. So when we do this multiplication, we have at the end 65,024 different IP addresses. So now, are IP addresses missing from the single network case where we only have one network? Well, before we had 65,534 different addresses, right? And now we have 65,024 IP addresses. So we've lost in total 510 IPs. However, we have gained a lot of flexibility because now instead of only one network, we can have lots of networks. We can have in total 256 networks, which is by far very more interesting than having only one single network, right? Only one single network. So subnetting is everywhere, not only with internet service providers, but it is widely used in computer networks.
Okay, so now let's see another example of subnetting. Now suppose that this range is provided and you want to determine a valid addressing for this network in here. So we have the internet and we have here these four networks and we need to use this range address. So here what is important is to know what is the number of networks that we need. As we know, we have four networks. So if we need four networks and we want to apply subnetting, we will need here to take 2 bits, okay? Because 2 raised to 2 will give us 4. So we will take 2 bits of the host ID and they will be passed to the subnet ID. Right, so from this range that we have here, from the 24 bits of the mask, we take here 2 bits of the host ID, okay, to be part of the subnet ID. Right, so essentially what we do is we play with these 8 bits or with the remaining bits of the host ID and we create here the number n of different networks. So as we can see now, the network 1 will be this configuration. Essentially we take what we took before, the first 3 decimal values. Remember that we will take the first 3 decimals because here we have a mask of 24. If we have a mask of 24, it means that the net ID originally is 24 bits, and we also know that each decimal number in here occupies 8 bits. So this is 8, now with this 16, with this 24. That's why we take here the first 3 decimal values. And also, okay, moreover, and in extension, we need to take these 2 bits in here to be part of the subnet ID. So they will also belong to the net ID of this network 1. Right, on this case, if we have here 2 bits, we can use 4 combinations. The first one is 0, 0, the second 0, 1, the third 1, 0, and the final one 1, 1. We do it for each of the network, a possible combination. Also note that now the host ID is reduced to 6 bits, right? Because initially we had 8 bits, we applied this reduction, okay, and we now have 6 bits for the host ID because we take 2 of the bits, we took 2 of the bits to be part of the subnet ID and therefore to the net ID of each of these networks as well. Now let's study the new masks of these networks. So the network 1 will have this mask. Keep in mind that here the mask will be of 26 bits for all of these networks. That's why we see here /26. And now what is very important, and most students here get confused, is when defining and representing these networks in decimal representation. So on this case, we have here these first 3 decimal values, 24 bits, and we take these 2, so 26 bits of the net ID, right? And then the final value of the host ID needs to be all zeros. Remember, every network address has all of the bits of the host ID to be 0, right? So if we have here 0, 0, 0, essentially all of the bits to be 0, 8 bits 0, this is the same as 0, okay, in decimal. That's why we have here the 0. Now, on the network 2, we use the combination of the subnet ID 0, 1. However, this combination 0, 1 is not placed at the end. It is placed here at first of these 8 bits. So now if we write this decimal, or in this case, this binary value, 0, 1, 0, 0, 0, 0, 0, 0, and we want to transform this binary number to decimal, then we only take this index 6 because it is the only index that has a 1, so 2 raised to 6. This gives us 64. So this value in binary, okay, is equal to 64 in decimal. That is why here we see the point 64. Okay, this is the reason, because this number, this 8-bit here, is transformed to 64. And then the network 3, since we use the combination 1 0, then this number will be what? Well, will be 828. This is the same idea, but instead of 0 1, now we have 1 0, and hence we only take here the power 2 raised to 7. This gives us 828, right? And finally, the network 4. Again, now we have the combination 1 1, all of the remaining bits are 0, so 1 1 is the same as 2 raised to 7 plus 2 raised to 6, so 828 plus 64. This number in binary is 892, right? Okay, so before coming to this conclusion in here, in red on the right, first let's study the broadcast addresses, okay, because this is going to be important, and then we will conclude this, or basically the number of hosts that we can have on each of these networks, right? So we begin with the broadcast address of the network 1. Remember that any broadcast address has all of the host ID bits to be 1. That's why here we see all of the host IDs to be 1. Now, keep in mind that here the subnet ID does not change. Here the subnet ID doesn't change if we are analyzing the network address, if we are analyzing the broadcast address, if we are analyzing the host ID address, and the address of an interface inside this network, it doesn't change because this is part of the net ID, right? So here we begin 0, 0, but then we have here, as we can see, 6 ones. So if we have 6 ones, and we need to translate this number, to convert this number to decimal, again, we write the indices from 0 to here, since we have 8 bits from 0 to 7, right? And we only take here the exponents that have a 1. So 0 has a 1, so 2 raised to 0, right? Plus 2 raised to 1, okay, plus 2 raised to 2, plus 2 raised to 3, plus 2 raised to 4, plus 2 raised to 5, and then the 6 and 7 will not be taken because they have a 0. So now when we compute the sum, 2 raised to 0 is 1, 2 raised to 1 is 2, raised to 4, in this case 2 raised to 2 is 4, 2 raised to 3 is 8, right? 2 raised to 4 is 16, and finally 2 raised to 5 is 32. We need to compute the sum now. This gives us 48 plus 84 plus 4, 58. So this is 56, then plus 4, 60, 61, 63. So the final result is 63. And that is why we see here on the decimal representation the value 63, right? And now if we take this combination, we do the same thing, but we also take here the power 2 raised to 6, right? So we sum 64 to this value. This gives us 827, the network 3 for the broadcast address. Now from this 63, we sum 2 raised to 7, right? Which is 828 plus 63. Which gives us 891, and finally, on this broadcast address of the network 4, the subnet ID is 11, and all of the host IDs, because by definition of the broadcast address, they are all 1 also, then we here have 8 bits, and all of them are 1. This means that the value will be 255. Okay, so once we have seen the network addresses and the broadcast addresses of each of these networks, okay, it is important here to consider, for instance, for the network 1, what is going to be the range of possible host IDs addresses that we can set and we can assign. Well, here from the network 1, we can assign hosts with the IP addresses from this one, which is here 209.0.14, and then we take 1 until 209.0.14 and 62. And why so? Well, because essentially if we analyze this configuration here, let's just analyze this configuration for a moment of the network 1. So as we can see on the network 1, we will always have the subnet ID to be 00, and then we have the remaining bits. These are 6 bits to the host ID, right? And they can be any value that are not 000000, because this is for the network address. So a host ID can have this value, and also a host ID cannot have this configuration because this is for the broadcast address, right? So we can also not have this value. So how can we calculate how many hosts? Very simple. We count how many bits we have of the host ID. So we have 6 bits for the host ID. Therefore, to calculate the number of hosts or the number of IP addresses is 2 raised to 6. And then we need to subtract 1 for the network address and also 1 for the broadcast address. This gives us 64 minus 2, which is 60. This is the number of different IP addresses that we can have, or the host IDs inside this network, essentially from 0.1 until 0.62. Keep in mind that 0.0 is not possible, because in that case 0.0 is for all of the bits of the host ID to be 0. This is the network address, and also all of the ones is not possible because this is the case, right? This 0.63 is not possible because this is the case that all of the bits of the host ID are 1, so the broadcast address case, right? So we have here 62 possible IPs addresses to set to these host IDs of the network 1. And then what about the network 2, network 3, and network 4? Well, the same number of hosts, because in all of these networks, the host ID, okay, has an occupation of 6 bits. And we also need to subtract the network address and the broadcast address of each of these networks. Therefore, all of these networks, okay, will have as a maximum 62 hosts, 62 different IP addresses to set for the hosts. Very well, let's study now a final example with variable masks. So this is going to be very important. So suppose we are given this range, okay, of the IP addresses. We have here this mask 24, this original mask, and we have 4 networks, this networking configuration. The network 1 needs to have 100 hosts, network 2 20, network 3 50 hosts, and network 4 20, right? So here, right, if we have 4 networks only, well, we already know the number of networks, so we'll need 2 bits of the subnet ID only, because 2 raised to 2 gives us 4, right? So initially, in principle, we could think that. So we can have here, with 2 bits of the subnet ID, 4 different networks, right? However, we have a problem, because if we take 2 bits of the subnet ID, then we'll have 26 for the net ID, and therefore only 6 for the host ID, because 32 minus 26, as we know, gives us 6 bits, as we can see on this example, right? We take 24 bits for the net ID, 2 bits for the subnet ID, and the remaining bits, only 6 are for the host ID. However, with 6 bits of the host ID, there are in total 2 raised to 6, right? 6 in principle here addresses available, and we can also need here to subtract 1 for the network address and 1 for the broadcast address, that they cannot be set for the host. So here with this example, we can only have 62 hosts. This is not enough for the 100 hosts that we need on the network 1. So how can this be solved? Well, this problem can be solved very easily, okay, and with practice you'll see that this is very simple. We have to use variable masks, and we will always start with the largest network and go in descending order. So we always recommend you to start here with a network that has the maximum number of hosts. If all of them have the same number of hosts, then you can start with any network. On this case, the network that needs more hosts is network 1. It needs 100 hosts, hence it is the largest network. So we will start with this one. What we need to take here into consideration? Well, on this network 1 that needs 100 hosts, right, we also need the network address, and we also need the broadcast address. And moreover, since we have a router connected to this network, this router is not a host, it is a router. Right? So here, this is an interface that we need to set. This is an IP address that we need to set. Remember that the router here always needs an IP address. This interface needs an IP address. So we also need here the IP address for the router. So in total, we'll have and we will need 103 IP addresses. So now the power of 2 closest to 103 that exceeds it is south. In this case, 2 raised to 6 gives us 64. This is not enough. Okay, this number of IP addresses is not enough. We need 103. So if we keep incrementing, 2 raised to 7, this gives us a value of 128, right? So this is enough. And to here, set these 803 IP addresses, we will need then 7 bits, right? We'll need here 7 bits of the host ID to address this number of hosts on the network 1. Okay, very well. Once we have finished with network 1, we now go to the second largest. So this is network 3 with 50 hosts. So now, if we have 54 hosts, we will also need the broadcast address, the network address, and this interface for the router. So in total, 53 IP addresses. Again, we need here to look the power of 2 closest to 53, and this is solved. So 2 raised to 5 gives us 32. This is not sufficient. 2 raised to 6 gives us 64. This is sufficient, right? So we'll need here to use 6 bits of the host ID for the network 3. So now, note, very important, pay close attention, because the network 1 will have 7 bits of the host ID, and the network 3 only 6 bits of the host ID. So they will have different number of bits for the host ID. This is because we are going to use variable masks. So now we go and we keep going with network 2. Okay, here we can network 2 or network 4 because both of them have the same size. So it is your choice. We opt for network 2. So we will need again 20 for the hosts, plus 1 for the network address, plus 1 for the broadcast address, and finally the last one for the IP address for this interface for the router. So in total 23 IP addresses. With the power of 4, this is not sufficient, 16, but with the power of 5, yes. 2 raised to 5 gives us 32. So network 2 will have 5 bits of the host ID. And finally, the network 4, it is the same idea. Since we have the same number of hosts requirement, the number of bits will be the same, right? We need here 23 IP addresses for the router as well, broadcast, network, and the hosts. 2 raised to 5 gives us a value sufficient to support this number of hosts, right? So 32 different IP addresses. So we also here need 5 bits of the host ID for the network 4. So all in all, 7 bits of host ID network 1, 6 bits host ID network 3, 5 bits network 2, and also 5 bits network 4. Good, so now finally let's study how these network addresses will be like, and also how these broadcast addresses will be. Okay, so now it is very important to remember that initially we had a mask of 24. We selected only the first 3 decimal values to be the net ID. And on the network 1, since here we have 7 bits of the host ID, then we will have only 1 bit for the subnet ID. Here we set this bit to be 0. And now very important, okay? It is very important that addresses do not overlap. So be very careful, because addresses must not overlap. What is overlap? Well, suppose here that on the network 3, that we know we have 6 bits of the host ID, and then we will have 2 bits of the subnet ID. What if we start here, okay, with 0? So what if we use a combination that we start the first bit of the subnet ID to be 0? Well, this will be wrong, because this is going to be overlapping with the network 1. In fact, if here you pay close attention, this value 0 of the subnet ID is at index 7 of this 8-bit number, right? This is index 0, 1, 2, 3, 4, 5, 6, 7. So we have a 0 at index 7. This means that this is going to be an identifier of the network 1. No other network can start with a 0, right? So we here use a 1. That's why we need to use a 1 on the network 3, right? 0 will be overlapping with the network 1. So here on the network 3, we have 6 bits of the host ID, and then we have 2 bits of the subnet ID, and we here use the combination 1, 0. So no other network, okay, regardless of the number of the subnet ID, no other network can have the initial combination 1, 0. Okay, this is an identifier of the network 3. So as we can see, 10 identifies this network, it is the subnet ID, and we also have here all of the bits to be 0, very important, all of the bits to be 0 of the host ID and all of these networks, because this is something that is by definition of the network address. Any network address has all of the bits of the host ID to be 0. So in the case of the network 1, if we have 8 zeros, we have the value 0 in decimal. In the case of the network 3,
we have 7 zeros and 1 1. This one is at index 7, so we basically do the operation 2 raised to 7. This gives us the decimal value 828. And then we come here to the network 2. Remember that on the network 2, we have 5 bits of the host ID, the same as the network 4. So if we have 5 bits of the host ID, this means that we have 3 bits for the subnet ID, right, of these 8 bits that we have here, this 8 bits space. So 3 bits are for the subnet ID. And here we use the combination 1 1 0. Why we don't start with 1 0? Well, because if we start with 1 0, this will be in conflict with the network 3. So we need to start with 1 1. So 1 1 0 identifies this network 2. And what is this decimal value? Well, basically 2 raised to 7 plus 2 raised to 6, essentially converting this binary number to decimal. Okay. Finally, when we arrive to the network 4, we also have 5 bits of the host ID, and then we have 3 bits for the subnet ID. We can start with 1 1 0 because this will be in conflict. This will overlap with the network 2, so we start with 1 1 1, right? And all of the bits of the host ID are 0 because this is a network address. So here we transform this binary number into decimal. So 2 raised to 7 plus 2 raised to 6 plus 2 raised to 5 gives us 224, right? Very important, the masks. So since we had initially on the network 1, right, and essentially on the range we had the mask of 24, on the network 1, since the subnet ID is 1, we add 1 bit, so we have 25. Then network 3, we originally had 24, but since here we have 2 bits of the subnet ID, we add 2, so 24 plus 2 bits, 26 bits. Network 2, we have 3 bits of the subnet ID, so 24, the original mask, plus 3 bits, 27 bits. So now the mask is 27. The same for the network 4, 24 plus 3 bits, 27 bits. This is our masks. So this is why we say that this is an example where we use variable masks, because each network can have different masks, and hence a different number of the subnet ID. So here the broadcast addresses are the same idea as the network addresses. The only difference is that now all of the bits of the host ID are ones by definition of the broadcast address. Keep in mind that now the decimal value is also changed, because now we need to transform this binary number to decimal. If we transform this binary number to decimal, this gives us 827. When we transform this one to decimal, gives us 891. This one to decimal, 223. And the last one, since we have all ones, we have 255. Very important. Note and pay close attention. The subnet ID doesn't change. The subnet ID doesn't change if we are analyzing the network address, if we are analyzing the broadcast address, or if we are analyzing the host address inside the given network, okay? If we have the network 1, any host that is inside this network will have the subnet ID here 0, right? If we are on the network 4, any host and any router interface that is connected to this network 4 will start with the subnet ID here 111. Okay, the only thing that is going to change are these blue bits of the host ID, but here the beginning is going to be the same. This is because this is the identifier of this network. It is how we identify that they are inside these networks. Very well, and with this we finish this last example using variable masks. Don't worry if this seems a bit complicated at first. As we practice with many problems and also solve exams, you'll see that subnetting is going to become very, very simple.